first of all, this work, I did this work with the collaboration with Professor Maiti, Professor Sriram Kumar, and one of my junior, Riazul Haq. So, so before the beginning, I would like to thank them, and I would like to also thank to the organizer for the invitation here. This is an opportunity to present my work in this platform. So this is an honor for me. Okay, so let's start. I will talk about decoding the reheating era through primordial gravitational waves. That means the title says a lot. Actually, we want to probe the reheating era, which basically connects the inflation to the standard Big Bang cosmology. We want to probe that era through primordial gravitational waves. So for a brief introduction, first of all, I want to explain what we know and what we probably do not know about cosmology nowadays. So what we know for sure that inflation, the universe starts from an inflationary era, which actually explains the initial stage of the universe. And there are a lot of success of inflation. First of all, we know that the inflation can solve horizontal flatness problem and also can generate, the most importantly, generate a scale invariant curvature power spectrum from quantum vacuum. And after the inflation, we also know the standard Big Bang cosmology very well. That is the radiation era and the matter-dominated era. And for the moment, forget about the dark energy era at the moment. Okay. So we know these things, what is inflation and what is the standard Big Bang cosmology. But what we probably do not know is the intermediate era between inflation and the standard Big Bang cosmology. So what we probably do not know is following. When do the normal matter fields create? Sorry. The answer is probably during the reheating era after the end of inflation. And what are the essential parameters to describe the reheating stage? Again, probably the inflaton decay constant. That means the constant by which the inflaton energy decays to radiation, and the reheating equation of state parameter, that is omega. So why these two parameters are essential for the reheating stage? Because the decay constant actually says when the reheating era ends, and the equation of state parameter actually says what is the velocity or what is the speed of the reheating era. I mean how fast the Hubble parameter evolves to the reheating era. So these two parameters are essential to describe the reheating era. However, we do not know the possible values or the possible constraints of these two essential parameters, gamma and omega. Gamma is the decay constant and omega is the equation of state parameter. I repeat, gamma actually says when inflation ends, and omega actually says how fast the Hubble parameter moves during the reheating stage. But we do not know the possible constants or the possible values of these two parameters, which actually says a lot about the reheating era. And next, we also do not know what is the actual mechanism for reheating era. So these two questions are very much important actually for the reheating era. That is, what are the possible constraints of gamma and omega, and what is the actual mechanism for the reheating era. So in today's talk, I will concentrate on these two questions particularly. I will describe how can we probe gamma and omega, and also how can we probe a possible mechanism of the reheating era through primordial gravitational waves. That is our main goal in today's talk. So I have already explained the motivations of this work. We have a clear motivation, that is to understanding the reheating era better. And as I explained in the present paper, we provide a way to decode various informations of reheating phase, particularly gamma and omega, through the primordial gravitational spectrum. So let's start. So this is the motivation. So let's start. I will briefly detail this three part in my today's talk. First of all, I will explain a brief about background cosmological dynamics, mainly about the reheating dynamics. And in the second part, I will describe, again briefly, the GW's energy density. And the third part, I mainly describe how can we probe the reheating era by gravitational wave spectrum at today. Okay, so the first part, this is the background dynamics. Very easy. We know that the action is described by the well-studied alpha attractor inflationary potential scalar tensor theory. This is the potential form when n has the value equals to 1. This is the potential of a Starobinsky. This is the basically Starobinsky potential, because the Starobinsky potential is a sub-candidate of this alpha attractor potential. You know that. So see, this potential has a plateau region at suitably large values of the inflaton field. So when the inflaton field lies in this plateau region, the inflation occurs. And when the inflaton comes out from this plateau region, the inflation actually ends. and then the reheating era starts. So this is the basics of this potential. Actually, when the inflaton field comes out from the plateau region, the acceleration term of the inflaton field starts to dominate, and that's why the inflation ends and the reheating era starts. So this is the basic action of our model. The inflationary dynamics, as I mentioned, this is the initial stage of universe. When the inflaton lies in the plateau region, the inflation occurs, and we take the de-Sitter inflationary scenario when the scale factor behaves like equation 1, where hi is the Hubble parameter during inflation, and eta is the conformal time. Next, come to the reheating scenario. This is the main part because we want to probe this phase. So this is the diagram where y-axis is the inflaton energy density, basically the co-moving inflaton energy density, and the x-axis is basically the time. So when h equals to hf, this arrow, the inflation actually ends. Now, as the universe expands, the Hubble parameter decreases, and when the Hubble parameter reaches to the inflaton decay constant, that is gamma, the inflaton energy density suddenly converts to the radiation. All the inflaton energy density suddenly converts to radiation, and that's why the reheating era ends. So this is the beginning of reheating era when h is equal to hf, that is the end of inflation or the beginning of reheating. And as the universe expands, the Hubble parameter decreases, and when it reaches to gamma, it indicates the end of reheating because all the inflaton energy density suddenly converts to radiation. Because when h is greater than gamma, the inflaton energy density does not decay because the universe expansion is much more larger than the decay constant. So when the Hubble parameter is around gamma, the inflaton energy density starts to decay. And based on this argument, we consider basically two scenarios. In one of them, the inflaton energy density suddenly converts to the radiation at the end of reheating, and in the other scenario, we'll consider the inflaton energy density gradually decreases, not suddenly. It gradually converts to radiation around h equals to gamma. So these two scenarios we'll consider. Okay. Again, I repeat because this is important. In the first scenario, the inflaton energy density suddenly converts to radiation when h becomes equal to gamma, and that indicates the end of reheating. So this is the period of reheating. Okay. In the first scenario, this is the period of reheating. The co-moving energy density remains constant during the whole reheating era. However, in the second scenario, we consider the inflaton energy density does not suddenly convert; it gradually converts to radiation around h equals to gamma. Okay. So by this two picture, you can guess that these two reheating scenario almost same, but gets different at the end of reheating, because at the end of reheating, the inflaton gradually converts radiation here, and here at the end of reheating, the inflaton suddenly converts. So this two scenario gets different at the end of reheating. Otherwise, this two scenario is basically same. So concentrate on the first scenario where the inflaton is suddenly converting to radiation at the end of reheating. Here, since the co-moving inflaton energy density is constant, there is no radiation during the reheating. The radiation comes at the end of reheating, and that's why the Hubble parameter evolves like this way in this first scenario, where omega is the inflaton equation of state parameter during the reheating era. And the end of reheating is actually dictated by this equation when Hubble parameter becomes equal to the decay constant, as I mentioned. However, in the second scenario, as I mentioned, that inflaton gradually converts radiation. So here, as I have written here, the inflaton gradually decays to radiation. However, here, the effective equation of state parameter is not equal to the inflaton equation of state parameter, because during the reheating stage here, the inflaton and the radiation concomitantly occurs. So the effective equation of state parameter is actually given by this expression where rho phi and rho r occurs. Rho phi is the inflaton and rho r is the radiation energy density. During most of the reheating stage, rho r is 0, because see, during most of the reheating stage, the inflaton energy density is constant and the radiation energy density is 0. Rho r is 0, and that's why omega effective equals to omega. So R1 and R2 are similar during most of the reheating stage, as I mentioned earlier. However, around the end of reheating, the radiation energy density is not 0, and that's why R1 and R2 gets different. So these two scenarios are basically same during the most of the reheating stage. However, at the end of reheating, when the Hubble parameter comes around the decay constant, this two scenario becomes different. Okay. So this is all about this two scenario. We want to probe this two scenario by the gravitational wave spectrum. For a brief, after the reheating, the universe enters to radiation dynamics, to the radiation era, where the equation of state parameter is 1/3, and that's why the Hubble parameter evolves by this way. Okay, so this is the background dynamics where the universe starts from inflation, then goes to reheating, then goes to radiation, and based on the reheating mechanism, we consider two different reheating scenario, R1 and R2. Now come brief about the second part, that is the what do you mean by GWs, or what do you mean by GW's energy density? Actually, here I will explain what is the observable quantity in regard to the primordial gravitational wave spectrum. So before going, I want to explain this diagram because it is important. In the y-axis, I have drawn co-moving Hubble radius, and in the x-axis, the e-folding number has been drawn, that is logarithmic of scale factor. This is the inflation era where the co-moving Hubble radius decreases with time. This is the reheating era, the fast increasing part of the co-moving Hubble radius. Then this is the radiation, and then the matter dominated. After matter dominated epoch, the Hubble radius again starts to decrease because of the dark energy era. I have concentrated on the three modes, that is KCMB, KRE, and KF. KCMB is the CMB scale mode, that is the large scale mode on which most of our observations lie. KRE is the mode, you can see from the diagram, which re-enters the horizon at the end of reheating. This is the end of reheating where KRE actually re-enters the horizon, and KF is the mode which re-enters or exits the horizon at the end of inflation. So we want to probe this era actually between KRE and KF, this reheating era. Okay. See, this era actually connects the inflation to the radiation era. So we want to probe this era by gravitational wave spectrum. And I will use these three modes frequently. So I have explained what are the three modes actually, KCMB, KRE, and KF. So please remember these three modes. It will help later. Okay. So finally, PGWs or primordial gravitational wave is basically the tensor perturbations over the FRW metric spacetime, and the tensor perturbation is gauge invariant. We know that. So Hij is the tensor perturbation variable, which depends on conformal time and the spatial part x. So equation of motion for this tensor perturbation is basically this equation: hk double prime plus 2a prime by a hk prime plus k square hk equals to 0. It is the Fourier decomposition equation actually. So hk appears where k is the Fourier mode, and A is the scale factor, the background dynamics. So it is evident from here that the tensor perturbation actually couples with the background dynamics. And this is the energy density for the gravitational wave spectrum, rho GW. We will concentrate on a quantity which is dimensionless and known as omega GW. This is the observable quantity, omega GW, which is basically observed, or we hope to be observed in various GW observatory. This is the so we are interested on this dimensionless quantity omega GW, which is basically rho GW by 3 mTL square h square, basically the critical energy density of the universe at that moment when we want to measure omega GW. So this is the quantity on which we are interested at the present epoch. So this is the basics of the tensor perturbation. So our strategy is following: we'll use this equation, plugging the background dynamics on this equation by a prime by a, and then want to solve the tensor perturbation equation at various epochs, at inflationary era, then at reheating era, then at radiation era. And coming all over the epochs, we will determine the energy density or the dimensionless energy density of the GW at present epoch. So this is our strategy. Okay. So I will come. So I'm coming to the third part, the last part. This is the most interesting part: decoding the R1 scenario by GW spectrum. Okay, this is the main finding of our work. As I mentioned, we'll solve the equation, tensor perturbation equation, epoch by epoch. So first come to the inflationary epoch. So plugging back the inflationary dynamics into the tensor perturbation and solve the tensor perturbation equation, and consequently we will determine the energy density of the tensor perturbation during the inflation. What we find is following: this is the tensor perturbation energy density during inflation, or during the super Hubble scale we can neglect this term and can write rho GW is proportional to 1 over a square during inflation. So it is evident that the co-moving energy density, which is basically A4 rho GW, basically increases with time during inflation. So this is the inflationary story about the tensor perturbation. Now come to the reheating part, when the tensor perturbation enters the reheating era, it follows a different equation of motion because of the background dynamics. And that's why the energy density becomes different. However, in the reheating scenario, just to come to the plot, in the reheating scenario, there are two kinds of modes, which is for the modes lie in this super Hubble region, that is between KRE and KCMB. Those modes actually are in the super Hubble region during the reheating stage. However, the modes in between KF and KRE lie within the sub-Hubble region at the reheating era. So depending on these two kind of modes, we get two different energy density of the gravitational wave, which is following. For the modes, for the large scale modes, which is between KRE and KCMB, rho GW follows this equation. That is same as inflation. It is expected because those modes do not enter to the sub-Hubble regime. That's why their energy density is basically same during the inflationary era. However, the modes which lie within KRE and KF, that is the modes which goes into the sub-Hubble regime, the energy density follows this equation. So basically, for K less than KRE, the co-moving energy density increases, and for K greater than KRE, the co-moving energy density becomes constant, but fluctuates or oscillates over a constant amplitude. So this oscillation is expected because those modes are in the sub-Hubble regime. Okay. Am I audible? Hello?
Yes, go ahead.
Okay. Thank you, David. Thank you. Okay, so this is the energy density of GW during the reheating stage. Now come to the radiation. It is very simple. We know that during the radiation era, when the modes are in the deep sub-Hubble regime, the co-moving energy density becomes constant, and this is the result of the rho GW during the radiation era. So we find the energy density during inflation, during reheating, and during radiation. And all over these epochs, we come to the present epoch and determine omega GW at present epoch. This is the result. This is the final result. Again, for K less than KRE, that is for large scale modes, we find that omega GW is scale independent, which is expected because in the super Hubble regime, the tensor perturbation becomes frozen. That's why the omega GW becomes constant for K less than KRE, that's for large scale modes. However, the most interesting modes are KRE. The most interesting modes lie within KRE to KF, because those modes actually goes into the reheating era. For those kind of modes, we find that omega GW is highly scale dependent, and the spectral index NGW depends on the reheating equation state parameter omega. This is very interesting. I repeat, for the modes which lie within KRE and KF, omega GW becomes scale dependent, and the spectral index actually takes this form, 3 omega minus 1 by 3 omega plus 1. So for omega greater than 1/3, NGW is positive, so it is blue tilted. For omega less than 1/3, NGW is negative, it is red tilted. And for omega is equal to 1/3, it is flat. It is the basically instantaneous reheating. And the plot is following. This is the plot. If we give a plot of omega GW, various and the frequency or the mode momentum K, we find this kind of plot. This is the KRE. Okay, when these plots get a break from flatness to blue tilted or red tilted, depending on the values of omega. So this is the KRE. See, for K less than KRE, the omega GW is actually flat. However, for K greater than KRE, omega GW becomes blue tilted or red tilted, depending on the values of omega, which is basically the reheating equation state parameter. So you can guess that by observing this kind of omega, this kind of spectrum, we can easily extract the actual value of omega during the reheating era from the slope. If we observe this kind of spectrum in the future observatory, because there is a hope to observe this, because you can see that some curves cross the observatory, like DCGO, BBO, etc., etc. So there is a hope to observe this kind of spectrum in the future, and if we observe this, then we can infer about the reheating equation state parameter from this kind of slope, because we know what is the expression of the slope, 2 into 3 omega minus 1 by 3 omega plus 1. So if we know NGW, we can extract omega. That means we can probe the reheating era by this spectrum. Recall the questions on which we're interested. We want to extract two quantities. One is omega and other one is gamma, that is the decay constant. So omega, the story of omega I have explained. How can we extract omega? And what is the story of gamma? See, this is the breaking point of the spectrum from when it gets blue tilted, red tilted. And this is KRE basically. This is the mode KRE, which re-enters the horizon at the end of reheating. From this information, we can extract gamma, because KRE is directly related to gamma. So these two informations actually infer about omega and gamma. From the slope, we can extract omega, and from the breaking point, we can extract gamma. That's what I've explained here. From the slope of omega GW, we can probe the initial value of the reheating piston parameter, and from the break, we can extract KRE or equivalently gamma. Now come to the last part, that is how can we extract the R2 reheating scenario. See, as I mentioned earlier, that R1 and R2 are basically same, but differs at the end of reheating. So you can guess that the spectrum will remain also same, but differs at the end of reheating. Remember, the KRE mode actually re-enters the horizon at the end of reheating. So the spectrum actually gets different around KRE, because that is the mode which re-enters the horizon at the end of reheating. And this is the plot of omega GW versus K in R2 reheating scenario. See, the plot is exactly same, but there is a burst of oscillation at KREZ, at K equals to KRE, because that mode re-enters the horizon at the end of reheating, and this two reheating scenario actually differs at the end of reheating. So this two kind of spectrum of omega GW in R1 and R2 reheating scenario gets different at K is equal to KRE by introducing some burst of oscillation. Again, from this spectrum, we can extract a lot about reheating error. From the slope, we can extract omega. From the breaking region, we can extract gamma. And from the time scale of this oscillation, which is very small, I know that, which is very small, but hopefully if we observe this time scale of this oscillation, then we can extract the time scale about how the inflaton decays to radiation during the reheating stage. Okay, so this kind of information can be extracted from this spectrum. And finally, by comparing these two kind of spectrum, we can conclude that if we observe some burst kind of oscillation, then it is the R2 scenario, otherwise it is R1 scenario. So by these two, by comparing these two spectrums, we can also infer about the mechanism of the reheating error. That's why I explained here. The absence or presence of oscillation will help to confirm the R1 and R2 scenario respectively. So just briefly I'm explaining, we want to answer two questions. First of all, what is omega and what is gamma? How can we extract them? And the next question is, how can we extract the possible reheating mechanism? Omega and gamma can be extracted from the slope or from the breaking region of PGW spectrum. And the reheating mechanism can be extracted by observing whether we can observe the oscillation or not. And see, again, in the R2 scenario, for omega greater than 1/3, when the PGW spectrum gets blue tilted, the spectrum can cross some of the observatory. So hopefully it will be observed in future, and we can infer about some reheating stage. Then this kind of information will be helpful to extract the reheating error. So finally, take-home message is following. The reheating error connects the inflationary universe with the standard Big Bang cosmology. However, our understanding the reheating error is still at its novice stage. So we provide a possible way to probe the reheating phase from GW spectrum. We basically discussed 2 points. We discussed how the GW spectrum can probe the equation of piston parameter omega and the decay rate gamma. And we also discussed how to probe a particular reheating mechanism by PGW spectrum, whether it is R1 or it is R2, by observing the burst of oscillation, whether it appears or not. Final point to be noted, because because I'm not explaining all of the details of this work. We also explained that how the PGW spectrum can be consistent with the recent nanograph data. I have not explained this, but if you're interested, if anyone is interested to see whether this is consistent with the nanograph or not, please see our paper. There is a nice explanation how this spectrum can be consistent with the nanograph data by introducing a late time reheating phase or blah, blah, blah. So this is all about my talk, today's talk. So thank you and have a nice day.